Welcome to today's Explainer. We are jumping right into a bold new framework that claims it's going to absolutely revolutionize how we adapt large language models. Look, if you've been following the AI space at all lately, you know that teaching a massive neural network new tricks is incredibly expensive, not to mention computationally exhausting. But what if all of that is about to change? Today, we're unpacking a fascinating piece of tech called NTK mirror. And honestly, if the claims we're about to explore actually hold up, it might just shift the entire paradigm of how we handle AI memory and behavior. Let's just dive right into the massive claim that recently sparked a pretty intense debate across the AI research community. Chlon from Sana Labs recently came out and stated the era of expensive, destructive fine-tuning is ending. I mean, that is a massive stake in the ground, right? The core suggestion here is that we basically no longer need to alter a model's foundational weights to teach it something new. It challenges the very foundation of how we've been modifying AI over the last few years. So this brings us to a really fascinating question. And actually, it's the hook for everything we're looking at today. What if the best way to train an AI is to just never actually touch it? How exactly can we teach an artificial intelligence new, complex behaviors, or give it new instructions without rewriting a single piece of its underlying neural code? Well, to answer that, we have to look at the pain points of how we're doing things today. Section 1. The problem with LoRA and our current limitations. To get why NTK mirror is turning so many heads right now, we first need to look at the very real bottlenecks in our current adaptation methods. Specifically, this sort of worst of both worlds dilemma that AI engineers are stuck in today. On one side, you have LoRA, or low-rank adaptation. It edits the weights of the model, and while it's super popular, it often causes what's known as catastrophic forgetting, meaning the model learns something new but forgets something old. Plus, it introduces high latency when you're trying to serve multiple users with different LoRA adapters in a SAS environment. Then, on the flip side, we have RAG, Retrieval Augmented Generation. Instead of changing weights, RAG just stuffs the prompt with information. But that inflates token costs, eats up your context window, and significantly slows down the generation process because the AI literally has to read all that extra text every single time. The crucial point here is that traditional fine-tuning can actually be physically destructive to the AI's existing knowledge. Just take a look at these numbers from a recent test. When engineers used LoRA on a model called Qwen 2.5-7b to teach it math, it added over 4 million parameters. But here's the kicker. It dropped 16.3 points on code generation. In other words, teaching the model math actually caused a sort of brain damage to its coding abilities. Traditional weight editing just severely struggles with clean multitask composition. Moving on to Section 2, how NTK mirror actually works through forward pass adaptation. So this new framework leans on a mathematical concept called Neural Tangent Kernel theory to sidestep weight modification entirely. It does this through a forward pass controller. Think of this like a super lightweight software plugin, or maybe a pair of specialized glasses you put on the AI. It's a tiny layer of multiplicative gates, just 50,000 scalars, applied to the AI's output activations while it's generating text. It alters the AI's output mathematically, but and this is absolutely key here, it leaves the original base weights 100% frozen. It doesn't rewrite a single parameter of the original neural network. Chronologically, here is how you build it. First, you completely freeze the transformer weights. Just lock them in a vault. Second, you learn these controller gates from examples, basically using a really neat mathematical shortcut to map the desired behavior into a tiny controller. And third, you simply attach these gates when the AI generates text. You're steering the activation space, modifying the signal as it leaves the model, rather than permanently changing the model itself. Section 3. The real breakthrough here? Persistent memory. Now here is the absolute Trojan horse of this whole framework. 200 kilobytes? That's literally the microscopic size of one of these controllers. It is so incredibly small that it unlocks an entirely new paradigm for persistent AI memory. Imagine having a highly specialized behavioral profile, like a specific coding style, a massive set of compliance rules, or a unique conversational persona that fits into the file size of a low-resolution image. This completely flips the script on how we handle memory. Right now, if you want an AI to remember a massive set of rules, you're stuffing the system prompt. That creates massive context token overhead and huge quadratic scaling costs. But with NTK mirror, memory is stored as these 200 kilobyte latent controllers. There is zero token overhead. You can encode documents, personas, or complex workflows as tiny plugins that attach instantly at runtime. The model doesn't even have to read the prompt. The behavior is simply mapped directly onto its outputs. And because these memory controllers are so incredibly lightweight and operate only on the forward pass, they compose cleanly. If you try to mix a math task and a coding task using LoRA, the base task degrades by 17% just due to interference. But with ntkmirror, the drift is practically zero. You can stack these memory controllers like Lego bricks without them ever stepping on each other's toes. Section 4. The Community Reality Check, where we evaluate these massive claims. Whenever a claim this huge drops, you know the AI research community is going to bring some rigorous mathematical skepticism, and rightly so. Take a look at this quote from researcher Rishi Gurnani. The NTK mirror duality is exact for one SGD step. Are you matching LoRA at convergence or LoRA at step 1? SGD means stochastic gradient descent, basically a single step of learning. This is a pretty massive technical caveat. The mathematical theory that makes NTK mirror work is perfectly sound for a single optimization step. But real LoRA fine-tuning relies on thousands of nonlinear steps to converge and learn deep, complex concepts. So the community is asking a very fair question. Can this tiny controller really mimic thousands of deep learning steps, or just the very first one? And that brings us to a super critical distinction. ntkmirror is absolutely fantastic at feature reweighting. It excels at amplifying or suppressing behaviors the model already inherently knows, like adopting a specific coding style or strictly following a formatting rule. But LoRA excels at feature creation, building deep, new neural pathways for entirely novel facts. A 200 kilobyte controller structurally might hit a ceiling when you're trying to teach the AI a massive corpus of brand new scientific data. It's like it tunes the engine perfectly, but it might not be able to build a brand new engine part from scratch. Section 5. The Future of Adaptation and Modular Architectures. So, considering the massive potential of zero-token memory and the architectural limits of feature creation, where does this tech actually fit into the future AI stack? Well, the consensus from the community analysis is that this might not be a universal replacement for all fine-tuning. Instead, it's more of a revolutionary leap for modular execution architectures. It's perfectly suited for creating persistent personas for AI agents, building coding copilots with highly specific workflow styles, overlaying strict operational rules for cybersecurity analysts, and handling dynamic routing in multi-tenant SaaS environments. It's all about swapping complex behaviors instantly and cheaply, without any of the bloat. To wrap things up, the era of massive weight editing is definitely not dead yet, especially for learning deep new facts. But the future of AI behavior and memory is undeniably becoming modular, lightweight, and incredibly fast. It leaves us with one really profound question to ponder about our own workflows. If you could attach a 200 kilobyte zero-token specialized brain plugin to your AI instantly, what behavior would you teach it? Definitely something to think about as you design your next AI system. Thanks for hanging out with me for this explainer, and we'll catch you next time.